So dear students, today we will discuss one of the important topic in material science, which is known as the single crystal. Single crystal material are very important in microelectronics and semiconducting industries. They are also essential part of optoelectronic industries. What do you think, students? What is the definition of single crystal? Basically, the single crystal materials are material which have no grand boundaries. They are basically defect free materials with continuous lattice. So these structures, the single crystal structures, are not broken at the edges, so they are defect free materials around their edges and anywhere, and that is the reason due to which these materials are unique in their physical properties such as optoelectronics, microelectronics and mechanical properties. So in this lecture we will briefly discuss about the importance of single crystal materials, how we can grow these materials, what are the core techniques through which we can produce defect free with no impurities and highly good in terms of qualities single crystals. Now coming toward the single crystal growth techniques, that how we can grow single crystals. Dear students, single crystal can be grown from the melt. Melt is basically a material which is heated up to a melting point, and when the material reached at the melting point, from at that time the single crystal is drawn from the melted material. So we will discuss in next few lectures that how we can produce a single crystal from melt. Single crystal can be grown from the solid. So there are a lot of techniques available from which we can grow single crystals from the solid. So we will briefly discuss them. Single crystals can be grown from the solution. Basically, the material which we want to convert into a single crystal is initially converted into a solution by using different types of solvent or different types of inorganic or organic types of chemicals, and by making them in or by converting them as a solution, and then we draw them from the solution in a single crystal. So we will discuss all those techniques through which we can basically convert a material into a single crystal from a solution in next few lectures. Single crystals can be grown from the vapor phase. So basically in vapor phase methods, the precursor or the material which we want to convert into a single phase is evaporated and then deposited with a specific orientation on the substrate to convert it into a single crystal. So we will briefly discuss this also. So now let's discuss that how we can grow a single crystal from melt. Dear students, there are different techniques available through which we can grow single crystals from the melt. One of the known techniques used to grow single crystal is known as the Zborowski method. In Zborowski method, basically a polycrystalline material is initially melted, and through using a different kind of single crystalline seeds as a template, these polycrystalline silicon dioxide basically or the silicon dioxide melt arrange itself with respect to the seed material and as a single crystal, and then they are drawn from the melt. So in this lecture I will briefly discuss about Zavorsky methods. Dear student, please note that there are certain limitations for the Zavorsky method. This method is commonly used for the growth of the single crystal of silicon. However, in case if someone or if anyone want to deposit a complex crystal structures or a compound crystal structures such as this crystal structure of gallium arsenide, they need to employ different types of crystal melt method. One of that crystal melt method is known as the Bridgman method. So this method may be employed horizontally, which is known as the horizontal Bridgman method, and it could be applied vertically, which is known as the vertical Bridgman method for single crystal growth. There are some other techniques known as Vernol method, zone melting method, in which in different point basically a solid or polycrystalline material is basically melted and then converted into a single crystal. And there is also another technique known as skull melting method. So in today's lecture I will only discuss initial and the first well-known technique, which is known as Zavorsky method. Now coming to the Zavorsky method. Zavorsky method is basically named after the Polish scientist known as Jan Zavorsky, who developed this method in 1916. This Zavorsky method has a broad range of application. It is widely used in commercial application, and because with this method we can grow a highly pure single crystal. So the range of impurity in using the Zavorsky method is in the range of 1 part per 100 billion. So that means that if we produce a crystal structure with 100 billion times, and only one time in 100 billion times there could be an impurity. This means that the Zavorsky technique can produce, or the Zavorsky technique produce highly pure single crystal material, and that is the reason this technique is widely used to grow single crystal in commercial and technological ways. Zavorsky method is known as the crystal puller mechanism. Basically, in this method, the material or the precursor or the polycrystalline material is melted initially, and then this melted material is pulled from its surface and converted into a single crystal. And that is the reason, that's why we call this technique a crystal puller mechanism. In Zavorsky method, a seed is used as a template and the single crystal is drawn accordingly. Okay student, this is very important to understand why seed is used as a template. Basically, in order to grow a single crystal in Zavorsky technique, it is highly important that we have a seed, we have a single crystal which act as a seed, and with this seed basically we grow a single crystal. So if the seed is basically a single crystal material, okay, so the seed has a specific orientation, it has a specific direction, it has a single crystal grain, it has a single grain boundary. So with respect to that grain boundary, or with respect to that, to the orientation or direction of seed, we will basically dip that seed into a melt of the polycrystalline material. So dear student, the seed is basically a solid, okay? It is a solid crystal, and when it is basically dipped into a melt, some point of the seed basically will be converted into light melt, but still there is a phase difference, okay? There is also a temperature difference. The seed is solid and the melt is basically in a liquid form, so there is a temperature difference in the melt and as well as the seed. So the melt will basically interact with a solid seed, and it will basically interact according to the direction of the solid seed, because the solid seed is single crystal and it has some relaxing or good points at which the liquid melt will be connected, and in this way the liquid melt will start to nucleate due to a temperature difference and convert it into single crystal. When the melt is basically converted into a solid phase, it is then drawn upward, and on due to which basically the other connected liquid will also start to convert into a solid phase, and in this way the whole structure is basically converted into a single crystal. So the seed in a single crystal is growth is very important, because the melt will start to orient in according to the direction of the seed material. Now, the precursor material used in Zavorsky technique, the precursor material is melt in a quartz line graphite crucible. Okay? Because dear student, you should know that the temperature of the precursor material, or the material which we want to convert, should be less than the melting temperature of the quartz crucible, okay? Because if the temperature, or if the melting temperature of the precursor material is higher than the crucible material, then the crucible material will initially convert it into a melt and will cause impurity in the whole single crystal. So it is highly important to introduce a precursor material, or material which we want to convert into single crystal, into highly melting temperature crucible, such as the graphite crucible, which has higher melting points than the 1400 or 1500 degrees centigrade. So the melt material, the precursor material is melted in Zavorsky techniques by using RF radio frequency heating at its melting point. The seed in this method is basically lowered into a molten precursor. The seed acts as a template and has a certain direction and orientation, and when it is raised slowly upward, result into a growth of the single crystal. So these are the key points of the Zavorsky method. Now coming toward the basic setup of the Zavorsky apparatus. Zavorsky apparatus consists of outer chamber and wall heating setup. Inside the wall heating setup, it consists of a furnace, and the furnace wall are basically used to control the heat inside the material which is present inside the Zavorsky apparatus. It has a solid arsenic or phosphorus gas inside the Zavorsky apparatus, because the solid arsenic or phosphorus gas inside the Zavorsky apparatus control the oxygen concentration inside the system, okay? Inside the furnace of the Zavorsky apparatus, there is a crucible holder. Dear student, you should note that the melting point of the crucible holder should be higher than the melting point of any material which we will use inside the Zavorsky apparatus. It should be greater than the melting point of the polycrystalline material which we will convert into a single crystal, number one. It should be greater than the crucible which we will use to put a polycrystalline material inside it. So usually in the Zavorsky apparatus, graphite crucible holder are used because they have a higher melting temperature, and their melting temperature is more than 1400 degrees centigrade. Okay, inside the crucible holder in Zavorsky apparatus, it has a crucible. Okay, usually the crucible used in the Zavorsky apparatus is a fused quartz, because this fused quartz is basically a highly compressed silicon dioxide. Okay, so they have very high melting temperature, and that is the reason they are used as a crucible inside the Zavorsky apparatus. And inside the crucible Zavorsky apparatus, we basically introduce a polycrystalline material. This is the material which we will convert into a single crystal. Student, here you should know that the polycrystalline material melting temperature should be lower than the melting temperature of the crucible, because if the melting temperature is of the precursor material or polycrystalline material is closer to the crucible material or is higher than the crucible material, then the crucible material will cause impurities inside the melt. Okay, so the material which is in the crucible will be transported into a melt. This will cause impurity in the structure, so impurity in the single crystal. So the melting temperature of the precursor or polycrystalline material should be higher, should be lower than the melting temperature of the crucible. And this system is basically connected with the magnet. I will discuss in few minutes that why this system is connected with the magnet. Inside the Zavorsky apparatus, it consists of a pulling rod. Okay, dear student, the role of the pulling rod is very important. Pulling rod basically draw a melt upward and convert it into a single crystal. And secondly, the pulling rod also rotate. Okay, it can rotate clockwise and it can also rotate anti-clockwise. It's depend on the manufacturer, so how he operate the pulling rod, in which direction he want to rotate it to convert a melt into a single crystal. This pulling rod basically is connected with a seat. Okay, the role of the seat in Zavorsky method is very important. The seat is basically template. Basically, it is a replica. So the melt will replicate the seat. So the seed is single crystal, and it has, as used in Zavorsky apparatus, is single crystal. It has a specific direction, it has a specific orientation, it has one grain boundary. So the melt will orient itself according to the orientation, according to the direction, according to the pattern of the seed. Okay, let me explain it in brief. So basically, in Zavorsky apparatus, seed is drawn, the pulling rod is basically drawn downward, and the pulling rod is connected with the seed. Okay, so it is drawn inside the melt somewhere here. Okay, now the seed material is solid, it is in solid phase, while the melt is polycrystalline, but it is in liquid phase, and the temperature of melt is higher than the seed. So the seed is solid and the melt is liquid. Heat will start to flow from melt into the seed. Okay, so and when the seed is pulled upward, okay, this, you know that the seed is solid, okay? There will be a slight change in temperature of the melt will cause a solidification and nucleation at the tip of the seed. So basically the temperature of the melt is higher and the temperature of the seed is less, and it is solid, so the heat is transported into the seed. Then the seed basically is pulled upward, the temperature slightly decreases more, and the melt temperature which is connected with the seed also decreases. It's basically converted from liquid into a solid phase at the point in which the tip of the seed is connected. So the melt is converted into a solid, and then the rod is pulled upward, so the continuously the melt, there will be a change in the temperature, and the continuously the melt will start to solidify, will start to nucleate and convert it into a solid phase, and then it is pulled as a single crystal upward. Okay, so dear student, it is very important to understand nucleation. Okay, nucleation is basically a phenomenon in which one phase is basically of material is converted into another phase. So the melt is in liquid phase, okay, the solid is seed is in solid phase, so they have a temperature difference, okay, and when the seed is pulled upward due to temperature difference, the connected melt will be converted into a solid phase, and when the connected melt is converted into a solid phase, basically they nucleate as a solid phase, and the nucleation start continuous because we are pulling rod upward and there is a temperature difference, so the crystal melt will continuously convert it into a solid single crystal, and in this way we draw and we produce a single crystal. Now coming towards the role of the magnet and the role of the rotation of rod. Okay, first let's discuss that what is the role of the rotation of rod. Okay, dear student, it is very important to produce highly uniform single crystal. So to get highly uniform crystal with a uniform diameter, industrialists basically rotate the pulling rod clockwise or anti-clockwise, and in this way they get a specific crystal structure with a specific diameter. Now coming toward the role of the magnet, that why these magnets at the top of the pulling rod and below of the crucible holder are used. Basically, dear students, it is very difficult for a single crystal to have different kind of dopant. The dopant may be p-type and n-type, but it is difficult for this method to incorporate a dopant into a melt and then convert them into a single crystal with all the dopant which are introduced in the melt. So for this, the industrialists use the magnets because the semiconductors basically interact with the magnetic field. The magnet causes a magnetic field, and they have a specific magnetic field line direction, whereas the semiconductors have electric field inside it, and they can basically, the magnetic field and electric field basically combined in the form of Lorentz force. Okay, and due to Lorentz force, the distribution of the distribution of the dopant basically become uniform, and in this way they are pulled upward with the seed and converted into p and n doped single crystals. So in next few slides we will briefly explain that how the p and n type of dopant may be introduced into a single crystal in the Zborowski methods. Now coming toward the processing steps involved in conventional Zavorsky method. Zavorsky method basically in Zavorsky method, initially the precursor material, the material which we want to convert into a single crystal, is melted. This material, the precursor material, is melted using resistive heating setup or radio frequency heating setup. As I previously discussed, the melting point of precursor or source material should be less than the melting point of the crucible material. Okay, so in this way they avoid impurity in the melt. Dear student, you should know that the melting material has different viscosity at different point. In order to get uniform melt material, the melt material is rotated. Okay, the centrifugal force of the rotation basically result the spread of the material uniformly, and in this way the quality of the melt material is improved. Next is the oxygen concentration is very important in Zavorsky method, and this concentration is basically controlled inside the chamber by controlling the pressure and flow rate of the argon inside the Zavorsky operating setup. After making the melt highly uniform and of good quality, the seed is basically moved toward the crystal melt and dipped it inside the melt a few nanometer. So now when the seed is basically connected and dipped inside the melt material, the pulling rate of the melt through the seed is very important. Okay, dear student, if the pulling rate of the melt is higher, this can cause defect and stresses in the single crystal. So the pulling rate is basically controlled in Zavorsky conventional setups. You should know that when the seed is pulled upward upward with respect to the melt, that can cause a nucleation. Okay, nucleation is basically done at the tip of the seed, because seed material is in solid phase, whereas the melt is in liquid phase. Okay, so the temperature of the melt is higher than the seed. That's due to this, the heat will start to flow from melt toward the seed, and the temperature of the melt at the point where the seed is connected decreases, result in conversion of the melt into a solid. Okay, and then this solid melt is basically a single crystal which is pulled upward, and in this way a continuous single crystal formation is done. Dear student, the pulling rate in Zavorsky technique is in the range of 1 millimeter per minute. So we cannot increase the pulling rate because this can cause defects in the structure. So in industrial and commercial application, it took too many months in order to produce single crystal with higher diameter and higher length or for production. The pulling rate is controlled by the crystal diameter, which is fixed in conventional Zavorsky operator setup. So basically the rod which is pulled upward in the Zavorsky operator setup is connected with the rotation setup. Okay, so the rod and the rotation of the rod is connected with the pulling upward, and in this way both these physical parameters are connected, and in this way we get a controlled single crystal. Comparing impurities at the interface, basically you know that the tip of the seed, there is a nucleation and single crystal is formed. So there could be impurities, and that these impurities are controlled by rotation, okay, and rotation of the crucible and seed, okay. So how the impurities can be controlled by the rotation of the crucible, okay. Since you know that the melt is in the liquid phase, it is in the liquid form. So and usually in general the viscosity of melt is different at a different point. So when the melt is rotated and when the crucible is rotated, the melt is rotated, and then the centrifugal force basically result in uniformity of the melt material. And next is the rotation of the seed. Rotation of the seed also cause the centripetal forces or centrifugal forces on the melt, which basically cause a uniform dispersion of the melt. So both the impurities are in the Zavorsky conventional apparatus is basically controlled by the rotation of the melt and the rotation of the seed. The control impurities of the melt is also done by uniform temperature, okay. So if the material has uniform temperature, if the melt material has uniform temperature inside it anywhere, then the viscosity of the melt material will be continuous over the whole region, okay. And secondly, the pulling rate is also important in order to control the uniformity, pulling rate, and the velocity, okay. So and the viscosity, sorry, it's pulling rate and the viscosity. So the viscosity is also pulling rate and the velocity, sorry. So the pulling rate and the velocity both are important. So if we are basically pulling the material with the faster rate, it can cause stretching inside the structure of the single crystal. The quality will be degraded, okay. So the velocity of the pulling should be in controlled fashion in order to get a uniform structure. Rotation and viscosity, as I have previously discussed, rotation play important role in the controlling the impurities inside the structure, and also the viscosity play vital role in controlling the quality of the single crystal. Now coming toward the diameter of the single crystal, that how in Zavorsky technique the industrialist basically control the diameter of the single crystal. They need a single crystal with specific dimension. That how the industrialist achieves a specific dimension. In industries, at industry level, the single crystal are grown in a diameter range of 300 to 450 millimeter. The latest reported diameter of the single crystal is in the range of 450 millimeter, and the maximum weight achieved till now is around 300 kg. So how the industrialists control this diameter and weight? The diameter and weight of the single crystal in industries is controlled by heating power, okay. It is controlled by a temperature inside the chamber, rotation of the crystal seed and the crucible, which is basically causing uniformity over the whole structure, also improve the quality of the crystal. Diameter is also controlled by pulling rate. The diameter of the single crystal is also controlled by the meniscus shape. Meniscus shape is basically a shape between the seed and the melt material. The diameter of the single crystal is also controlled by the weight of the crystal. So you know, if the weight of the crystal or is varying in the melt, and the pulling system is basically pulling the melt in a solid phase upward, with that can cause the if the melt is not uniform, that can basically affect the diameter of the setup. So the weight of the crystal is important in order to control a single crystal diameter. The viscosity of the melt is also important in order to control single crystal diameter. Concentration of the dopant in the melt is also important in order to control a diameter. Every dopant have its own mass, and if the concentration of the dopant is different in the melt material, there will be a variation of viscosity inside the melt, and that can affect the crystal diameter which we want to achieve. So the concentration of dopant in the melt is very important in order to control the single crystal diameter. Now coming toward the distribution of dopant. How industrialists achieve p-type dopants and n-type dopants inside the single crystal. You should know that the ratio of concentration of an impurity in the liquid to the concentration of impurity in a solid is segregation coefficient. And segregation coefficient is very important in order to introduce P and N type dopant inside the single crystal. So industrialists basically consider the concentration of impurity in liquid, basically the concentration of dopant in the liquid, to the concentration of impurity in the solid. Dopant concentration in a crystal is different from the dopant concentration of the melt. Okay, so crystal, it depends on the material, but dear student, you should know that the concentration of dopant is different in the crystal to the melt. It's depend on which phase is favorable to enhance the dopant, to incorporate the dopant. So it is not important that if we want to produce a single crystal with higher concentration of dopant, we basically introduce higher we basically put higher dopant into melt, but it is not important that all the higher dopant are basically transformed into a single crystal. So in both phases have their own dopant concentration properties. So the dopant concentration in crystal could be different from the dopant concentration in the melt. So dear students, now let's discuss that how in industries the conducting dopant uniformity is controlled during single crystal growth. Usually you see different types of P types of dope materials and N type of dope single crystals. So how the industrialists basically control the distribution of P and N type dopant inside the single crystal? This is basically done with magnetic field. As you know, according to the Lorentz equation and as you know the basics of the electromagnetic waves, the electric field in the electromagnetic wave, which is perpendicular to the magnetic field. So If the electric charge is moving toward this direction, magnetic field component is basically along this direction. They are along the 90 angle to each other. This results in spiralation. This results in deflection of the conducting dopant and semiconducting material. So, the Lorentz force is basically the accumulative or the combined force of electric and magnetic field. So when this electric charge is basically move inside the magnetic field, whether it is along inside the plane or outside of the plane, result in deflection of the electric charge. This is the concept of the distribution of dopant in the Zobrodsky method. So they basically use the magnetic field, okay, and magnetic field across the chamber of the Zobrodsky setup, which basically cause the deflection of the dopant and deflection of semiconductors, and which result into a uniform distribution of the dopant. You should know that it is very difficult for dopant to be distributed into a melt, and this is the reason that's why the conventional Zobrodsky setup use the magnetic field. They use, in order to get highly uniform distribution of the conducting dopant in the melt, the industrialists use stationary magnetic field. Basically, magnetic field is stationary throughout the chamber of the Zobrodsky apparatus, and in this way the dopant basically throughout the chamber basically uniformly distributed in the melt and as well as in the single crystal. However, in some industrial point of views, some industrialists need a variation of dopant at different point, so they use variable magnetic field. Magnetic field at one point is different than other point, so at the point at which the magnetic field is different, there will be a different concentration of the dopant. So it's depend on the industrial requirement, it's depend on the technological requirement. We can achieve different properties in the same material by distributing dopant in a different ways using a variable magnetic field. The dopant distribution can be controlled in a certain region. The industrialists use time controlled magnetic field. So let's say the pulling rate of the single crystal is 1 millimeter per minute. So the industrialists want the dopant distribution up to 1 millimeter. So they set a magnetic field for 1 minute, and in this 1 minute only 1 millimeter of this single crystal is basically have a dopant with a certain distribution, and when this magnetic field is shut up or is closed, there will be a no dopant concentration in the single crystal. So dear student, magnetic field play a very important role in order to distribute dopant inside the semiconducting single crystal. They can basically distribute the dopant uniformly. They can control a dopant into a certain region, and they can basically distribute a dopant point to point by using the variable or time dependent or stationary magnetic field. So now coming toward the segregation coefficient. Dear student, you should understand that it is very difficult to introduce a dopant inside the melt and form a single crystal. So the segregation coefficient is less than 1. This means that it is around, for boron it's around 2 into 10 raised minus 1. For aluminium it is around 2 into 10 raised minus 3. What this means? This means that the single crystal are not favorable to dope or to introduce or dopant inside them. So that's why the different types of magnetic field or different types of setups are introduced to incorporate dopant inside the single crystal. Most of the cases, if you see here in the table, most of the cases the segregation coefficient is less than 1. So the single crystal do not favor to incorporate the dopant inside them, and the dopants are basically rejected into a single crystal structure. And that's why conventionally or most commonly magnetic field is used to introduce a dopant inside a single crystal. So melt is basically progressively enriched with impurities via magnetic field. So for today, I think this is enough, and let's see, we'll discuss. I think this is for today. I think it is enough. In next lecture we will discuss about the Bridgman method and what are the types and importance of Bridgman method, why it was introduced in place of Zavorsky method. Thank you for today.